Alright, in the previous video we treated Coulomb's law of electricity. We used that law to determine the electric force that a charge exerts on another charge. Is that okay? Now in this video we're going to look at multiple source charge and the principle of superposition. Now first we'll start by explaining the concept of source charge and test charge. Okay, it's not like it's something from the space, something difficult to understand. A source charge is simply that charge that exerts, that creates the electric force which affects another charge. That another charge that is feeling the force, that is being affected by the force, is called the test charge. The one producing that force is called the source charge. So it is possible for us to have more than one source charge exerting forces on just one test charge. We shall represent a test charge with capital letter Q and then source charges with small letter q. Please just quickly look at the board here. I am using these dots, for example, to represent our source charges. How many are there? 3, is that not so? And then we have just one test charge. Clearly, you'll agree with me that each of these source charges will exert a force on what? This test charge. This one will exert a force on it. This will exert a force on this. And this one will also exert a force on that test charge. How many forces? 3. So what we're trying to do here, according to the principle of superposition, look at it. If you are able to calculate the force of each of these source charges on this test charge, then all you need to do is add them up. That process of your adding them up vectorially is what we refer to as the principle of what? Superposition. Now on the board we have the equation showing that this equation is simply Coulomb's law. Is that okay? Of electricity. The only thing now is that, just like I explained here, the test charge will be constant, only one of it. And because it is constant, that is why we had to bring it, and instead of using it to multiply this Q. Since it is constant, if you add in a constant term, you can factorize that constant out. Because only one of it. Now the source charges are more than one. They are more than one. That is why we introduce this summation sign, meaning add. You're going to add Qi all over Ri squared. This Qi, the idea, just like I defined, Qi means the ith source charge. That is it source charge number 1, source charge 2, source charge 3. So the I represent 1, 2, 3 as the case might be. Of course, the distance, just like you see, each of the source charge has its own distance away from the test charge. So just use this formula and then you resolve everything. We're going to apply it in our next video when we solve questions for us to see how we use it. I believe it is very simple. Alright, so we have this example on the board. It's going to help us to understand how to apply the principle of superposition and the concept of multiple source charges. That's the question. Charges are placed at the corners of the square of side A as shown below. So this is the diagram. Is that okay? This is the diagram. Now we are asked if Q is equal to 1.6 times 10 to the minus 19 coulomb, A is equal to 10 millimeter. Calculate the resultant force at the lower left corner of the square and its direction. Calculate what? The resultant force at the lower left corner. Now I'm going to ask you this question because it's very important for us to identify something. If you are calculating the resultant force at the lower left corner, where is the lower left corner of this square? Is it at point 1, 2, 3, or 4? Now if you position yourself and look at it, you agree with me that the left is 1 and 4. Then the lower is 4. Is that not so? So we are calculating the resultant force at this point. Therefore, our test charge will be here. The point is that every other charge is exerting a force at this point. So they want you to get that resultant force there. Is that okay? That being the case, positive 2Q will be our what? Test charge. Every other charge will be our source charge. As explained earlier, what do you need to do? Use Coulomb's law of electricity one at a time to calculate the force between one of these source charges and this test charge. When you are done, you resolve something and add vectorially. Is that okay? Now let us quickly look at how we go about it. The first thing, you convert this 10 millimeter to meter. And if you do that, you divide 10 by 1000. That's the change from millimeters to meters. You're going to get 0.01 meters. Is that okay? As our distance. Alright, having identified our test charge, let's move on now. I want to proceed to calculate the force of this charge 1 and charge 4. And remember, charge 1 is 3Q, so it's going to be what? F14 equal to, you know Coulomb's law formula? Look at it here. So it's going to be 1 over 4 pi A naught times Q1 on Q4. Is that okay? Times Q4 divided by square of the distance. Putting the value, this constant is 9 times 10 raised to the power 9. Then Q1 is what? Look at charge at point 1 is 3Q. See the substitution? Then times Q4, our test charge. Look at it, charge at point 4, which is 2Q. You can see that? Divided by square of the distance, 0.01 square. Please don't forget this Q has a value of 1.6 times 10 raised to the power minus 19. So you need to substitute that 1.6 times 10 raised to the power minus 19 here. And then punch your calculator, solve, you get F14 to be equal to, first, this way you're going to get 138, okay, that's 1,382,400, then times 10 raised to the power minus 19. Now I have to standardize it. To put it in standard form, I move this point down to between 1 and 3. If you move the point to the left, between 1 and 3, how many times? If you do that, let me just show you quickly. 1, 2, 3, 4, 5, and 6. So the point will come here 6 times to the left. So you're going to add 6 to minus 29. If you do that, you get minus 23, 1.3824 times 10 raised to the power minus 23 Newton. We've calculated the force of charge 1 on the test charge 4. All we need to do is to repeat the same process. You come here and calculate the force at this point 2 on this test charge. But on the board here, I actually calculated for 3 on 4 first. Is that okay? There is a reason why I did that. To get the force of charge 2 on this charge 4, you need to know that the distance is this diagonal. Are you seeing it? The distance is this diagonal, which means we are going to use Pythagoras theorem to get this. I'll label it as R. We're going to use Pythagoras theorem to get it. This is A, already this is A, so you can use Pythagoras theorem because this is a right angle triangle. So I had to calculate this one first, where the distance is simply A as well too, which is 0.01 meters. So I had to calculate this one first, where the distance is simply A as well too, which is 0.01 meters. Look at it on the board here. If you are calculating the effect of the force of this point 3, which is minus 2Q on plus 2Q, using your Coulomb's law, you can see that this would be something like Q3, is that okay, times Q4, because it is the force of charge at point 3 on charge at point 4 you are calculating now. So if you substitute minus 2Q, remembering that Q is 1.6 times 10 raised to the power minus 19, then times plus 2Q, look at it. Simplify and then you will get this as a final result. First you get this, if you move your points to standardize, you get this. It's important you make their powers to be the same. Is that okay? That's the essence of moving the powers. Moving the points rather from here. Okay, the next is to obtain our F24. This time around, the force of this charge on this. Is that okay? Now if you look at this source charge, it's a diagonal relationship. The distance is diagonal to our test charge. So calculating your R using Pythagoras theorem, you know, to be R squared equal to A squared plus B plus this A squared. And then if you want to get your R, you take square root of both sides. Remember first I told you is R squared equal to A squared plus another A squared using this side. Is that okay? So taking square root of both sides, your R will give you square root of A squared plus A squared, which is what you have here. If you add these two, you get 2A squared, or square root. Then using the knowledge of surd, you solve this. You know that is going to be, let's see that, square root of 2 times square root of A squared. That's what you're going to get. Then this square root will cancel this square. So everything will be root 2 times A, which is A root 2. Substitute, our A is 0.01 times root 2. If you solve that, this is what you're going to get as the distance between this charge and this test charge. Repeat the same thing by substituting. Okay, so using Coulomb's law, F24 is equal to 1 over 4 pi A naught, which has this value, then times Q2 on Q4. Is that not so? And then Q2, what is the value of the charge? Minus Q. So look at it. Then times our Q4 was the charge? 2Q. Is that not so? I seen that? Divided by square of the distance. The distance apart has been calculated to be R, which is 0.01414. You see that? Square it and simplify. You will get this at the end of putting it in standard form. So we are done with this. I have this first diagram. We're just done with solving this. We've not gotten the resultant force. Is that okay? Now, from this first diagram, how did we get it? I will quickly show you. Now, if you look at, this is positive charge and this is positive charge. So there is repulsion. This one will be pushing the test charge away. And that is why you can see the arrow facing down. That is F1 on 4. Then if you come to this is negative charge, this is positive charge. So there is attraction. This will be attracting this charge to itself. So you can see it. Then when you come to this diagonal point as well too, this is negative, this is positive. So this charge will be attracting this test charge to itself. And you can see that. The angle here is 45 degrees because this is what? A square. Square, this whole angle is 90 divided by 2 by this diagonal. Here will give you 45. So take note of that. And that is why I did that here. Now we're going to take a break. When we come back, we will now look at how to resolve this. You do force resolution into X and Y direction. You're welcome from our break as we round off our calculation of question number 1. Recall that before the break we had this diagram and it was explained. So all we need to do now is to resolve all these electrostatic force vectors. Is that okay? Into horizontal and vertical component. Okay, how to resolve vectors into horizontal and vertical. It's likely things that we have idea of already and we're going to work on it. The secret is simple. If you're resolving in horizontal direction, you multiply the force vector, the vector given to you, by cos theta. Then if you are resolving in the vertical direction, that is y direction, you multiply the force vectors by what? Sine theta. Remember that the theta there is best measured from positive x-axis. You can see this is our positive x-axis. So the theta we are talking about is measured from that positive x-axis down to the vector. Then you stop and get the value of the angle. But first, before we go through this, remember this horizontal is 0 degrees, this is 90 degrees, this is 180 degrees, and this is 270 degrees. Back to this place, which is 360 degrees, still giving you 0, okay? So these are the forces we obtain, F14, F24, and F34. So let us now resolve them using this diagram. So I will resolve first in X direction. So what will it be? I will come here. F34 cos 0. Remember that it's line on the horizontal here, so it is cos 0. Then plus F24. F24, the angle it made with the horizontal is 45. You can see that, right? 45 degree with positive x-axis. So it's going to be F24 cos 45 degrees. You see that? Then plus, you come here, F14. You see this one that I even wrote here is not necessary. F14 cos 270. This is purely vertical. It does not have a horizontal component. But I just have to indicate it so you will see the full calculation. If you punch cos 270, you get 0. So the horizontal component for this does not exist. Alright, so that's that. Substitute, you know your F34 and F24 already. So take your time and substitute. Cos 45 will give you 0.7071. Alright. Cos 0 is 1. Cos 0 is 1. 1 times F34 will give you the value of F34. So working this out, you're going to get our Fx, that is force in horizontal direction, to be 1.0846 times 10 raised to the minus 23 Newton. Proceed and resolve in vertical direction. Come back here again. Start with F34, this time sine 0. You can see that. Then plus F24 sine 45. And then plus F14 sine 270 degrees. Work around that. This F34 sine 0 is 0 because sine 0 will give you 0 times F34, 0 goes off. Sine 45 is 0.70771. Value of F24, we have it already, so you substitute. Then plus F14, F1 for this is the value times sine 270. Sine 270 is going to give us what? Minus 1. So simplify this out, and this is the Fy value first in the vertical direction you're going to get. So all you need to do now is to resolve these two forces into getting the resultant force. Is that okay? Because this is what we have obtained. This is Fx and this is Fy. The resultant now is the diagonal resultant force. Now the angle that the resultant force made with the horizontal will give us the direction of the resultant force. Now how do we get the resultant force? Simply Pythagoras theorem. Resultant here, Fr is going to give us square root of Fx squared plus Fy squared. And that is what I did here. If you substitute into this formula, is that okay? So work on that, solve it out, you're going to get your resultant, the resultant to be 1.6319 times 10 raised to the minus 23 Newton. And that is our resultant force acting on the left lower corner of the charges. In conclusion, we get the value of the direction of the resultant force. Remember, I told you that the direction of the resultant force is the angle that the resultant force makes with what? The horizontal. So we're going to calculate theta here. And how do you get theta? You use tan. If I step down this is our opposite and this is our adjacent. Opposite is Fy, adjacent is Fx. You can say that. So using your TOA, theta will be tan inverse Fy over Fx. Fy, we have the value already, look at it. Times 10 raised to the minus 23, you substitute. You notice that I didn't use the negative sign, it's not important since it is absolute value we are getting here. Is that okay? Then divided by Fx. Look at the value of Fx. If you substitute these values here, the 10 raised to the minus 23 will cancel out so that you'll be left with this. Use a calculator and obtain the tan inverse of this, and your result will be 48.35 degrees. So that the resultant force acting at the left lower corner of the square, having these charges, is in the direction 48.35 degrees from the positive x-axis.